So section 12.7, our objective is to use properties of similar solids to determine surface areas and volumes of solids. Alright, so the similar solids are two solids of the same type with ratios of corresponding linear measures such as equal ratios of corresponding linear measures such as height or radii. So, for example, you can see that like this in these two shapes, to tell if they're similar, I would say 7 matches up with 21. 7 over 21 is 1/3. The 5 matches up with 15. 5 over 15 reduces to 1/3. The 3 matches up with the 9. 3 over 9 is 1/3. All three dimensions of the rectangular prism have the same ratio, right? If that's the case, then they are similar solids. Everybody get the idea? All right. Theorem: if two similar solids have a scale factor of A to B, then the corresponding, this is the key part of the lesson, if their scale factor of their sides is A to B, if the scale factor of their sides is A to B, then the corresponding areas have a ratio of A squared to B squared. And the volumes have a ratio of A cubed to B cubed. So if you know one of these ratios, right, then you can find the ratios of the other measurements. So if you know scale length, which is your scale factor, if you know that's A to B, then you can determine the ratio of the areas, A squared, B squared, and volumes, A cubed, B cubed. If I know the ratio of the areas, A squared, B squared, I can take the square root, find the ratio of the sides, or I can multiply times A and B again and get the, well, then I'd have to cube this A and B to get the volume, all right? And so on. So here's a summary of that. If the parts have a ratio of A to B, the perimeters have a ratio of A to B, the areas have a ratio of A squared to B squared, and the volumes have a ratio of A cubed to B cubed. So in this case, the areas of these two, since it's a 1:3 ratio, the areas, so we had side length was 1:3, so area is going to be this squared, 1 over 9, and volume is this cubed. So 1 cubed is 1, 3 cubed is 27, 1 over 27. I know the different ratios. Tell whether the given rectangular prism is similar to the right rectangular prism as shown. All right? So here we're given a prism with sides 4, 2, and 2, right? And we have to determine, is this similar to that prism? Aaron, you're shaking your head no. Why not?
It's two of the same side, so two of the same measure.
Yeah, it's got, this one has 2 and 2, this one has 4 and 2 and 8. So there's no way it's similar. That's right. What about 6, 3, and 3? Is that similar to 4, 2, and 2? Well, we can compare these 2 to 3. That's reduced. We've got 2 over 3 for one side. And then we've got Here we've got 2 to 3. And here we have 4 to 6, right? 4 to 6 is equal to 2 to 3. So do they all have the same ratio? Yes, they do. So these two would be similar. B and the model are similar. Any questions? So that's just going through step by step what we did. They're not similar, and then these two are similar. Use a scale factor of similar solids. The cans shown are similar with a scale factor of 87 to 100. Find the surface area and volume of the larger can. So we're assuming then these would be for the smaller can. This would be S1 and V1. So we know the surface area and volume of the smaller can. We have to find the surface area and volume of the larger can. So here's how we do it. Okay. So we have the parts have a ratio of 87 to 100. All right. Their perimeters will have a ratio of 87 to 100. Their areas, we square the 87 to 100. The areas have a ratio of 7569 to 10,000. The volumes have a ratio of 87 to the third over 100 third to the third. So the volumes have that ratio. I don't square this again. I go back to the original, 87 over 100, and I cube it. Okay? 87 cubed, 100 cubed. Everybody know how to cube on their calculator? I think we tried that before, right? Make sure you can cube something on your calculator. On the graphing calculators, you do the math button. On the standard calculators, it's probably like an X to the Y button. It might have an X to the third, but there may be an X to the Y button. Okay, so you have to know how to cube on your calculator. In fact, why doesn't everybody go get their calculator out and see if they can do 87 cubed? Let's make sure everybody can do it. 87 cubed. If in doubt, you can just take 87 times 87 times 87. If you don't know where the button is, you can just multiply 87 times itself 3 times. Do that manually rather than, using the X to the Y button. There are?
Yeah.
So does everybody concur with that? So how many zeros should there be?
Should be just 1 million.
Just 1 million? Okay, that makes sense, yeah. Okay. So we'll cross out those last three. All right, so everybody is able to cube. All right, now, so here's why we're doing this, showing the ratios of the different measurements. Because what I can do is, so I have this surface area. All right, we have the surface area. So we have 7,569 over 10,000. That's the ratio of the areas. So that's going to equal to, so this is the surface area of can 1, so we would put that on top, 51.84 over x. We have to find the surface area of the second shape. Right? So we cross multiply and solve. Everybody see what I'm doing? I know this is the ratio of the surface areas. I know one of the surface areas. I know the smaller can. If I'd known the larger can, I would have put that on the bottom. But I know the smaller can. So that goes with the 7569. And then we have to find x. Cross multiply, so what do we get? What do we get for x? What's the surface area of can 2? Say again? 68? 68.49 inches squared. All right, sounds good. Any questions? Okay, let's do the volume now. So for the volume, we've got 1,000,000. So it's going to be, we take 658,503. We put that over 1,000,000. And we set that equal to 28.27 is the volume of the small can. We have to find the volume of the large over x. Cross multiply and solve. Somebody tell me what they got for this one. What do you get for this? X equals what? 23.9? 42.93 inches cubed. That sounds right as well. Everybody see what we're doing? Any questions? Okay. Let's check and see if we had the right answers. So 68.49, that's what we said, isn't it? Okay, and then for the volume we had 42.93. Yes. So we got it right. Okay. The pyramids are similar. Pyramid P has a volume of 1,000 cubic inches. Pyramid Q has a volume of 216 cubic inches. Find the scale factor of P to Q. So scale factor is like the ratio of the sides. So we know the volumes. We've got P and Q. So we have 1,000. And that's over 216, right? We have to find the scale factor of P to Q. So what do you think I need to do to these numbers? These are the ratios of the volumes. We need the ratios of the scale factor, which is the ratio of the sides. Yes? Not square root. You're on the right track, though. What?
Cube root.
Cube root. So practice on your calculator. Cube root of this and the cube root of that. What are the cube roots of those two values?
6 and 2. Or 2 and 6.
All right, so it's going to be the cube root of 1,000 over 216. You say it's 10 and 6? All right. So the ratio of the scale factor is 10 to 6. Is everybody able to do cube root on their calculator? If not, I'll come around and show you. It's this one, the x with the, so it would be, I think it would, you would do 3. Oh, I didn't do second. 3 second that cube root of 216. Right, cube root 216. Enter 6. Anybody else need help? All right. Yep, and you should always reduce the fraction. 10/6 reduces to 5/3. So the scale factor is 5 to 3. A storage sells balls of yarn in 2 different sizes. The diameter of the larger ball is twice the diameter of the smaller ball. If the balls of yarn cost $7.50 and $1.50 respectively, which yarn is the better buy? All right. So diameter is a length. So what we would do is, on this problem, we would have to get the scale factor. Okay, so that's step 1. Oh, okay. So they must sell the balls of yarn by volume. They should tell you that, because I didn't know whether balls of yarn were sold by diameter or what, but they're sold by volume. So if the diameter of the larger ball is twice the diameter of the smaller ball, then the scale factor is going to be x over 2x. I can, right? It's x over 2x. I can simplify that though. What can I simplify x over 2x to? We can get rid of the x's. What's it simplify down to? It's a 1 to 2 ratio, right? You can even bypass this. If one's twice, the diameter is twice the other one, we could just say it's, it's 1 to 2. So the scale factor is 1 to 2. We have to do the ratio of the volume. So what do I have to do to 1/2? Cube it. What is 1/2 cubed? Yeah. 1/8, right. 2 times 2 times 2 is 8. 1 times 1 times 1 is 1. So we have the volumes are, okay, they have it large over small, so it would be 8 over 1. Okay, so the volumes is 8 to 1. The next step, we compare the prices. The price of the large ball is $7.50 to $1.50. That reduces to 5 over 1. Right? So then, which one do you think would be a better buy? If the volumes are 8 to 1, but I'm paying 5 to 1, what's the better buy? So the volume of the second one is 8 times the volume of the first. The price of the second is 5 times greater than the price of the first. So which one am I getting a better buy with? Yeah, the large. Okay, I'm only paying 5 times more. I'm getting 8 times more. So we compare the ratios. And it works out that the larger one has a lower price ratio, so that's a better buy. Questions? All right? All right, so that's it for the notes.